session. Hi, everybody. This is the session TS2 from SIBGRAPI. In this session, we will have 5 interesting papers related to the computer vision area. For each paper, we will watch a short video about 5 minutes, and then we will open for questions and answers for around 5 minutes for questions. If you have any questions during the video, while we are watching the video, please post on the YouTube, or you can send it by the WOVA system. I hope you enjoy this session. Let's watch the first video related to the paper entitled HTR Floor, a deep learning system for offline handwriting text recognition by Byron Bezerra.
Hello, everyone. I'm Professor Byron Bezerra from the University of Pernambuco in Brazil. Now I will present in the International Conference on Graphics, Patterns, and Images, SIBGRAPI 2020, the work developed by my advised student Arthur Flor with other colleagues, which is entitled HTR Floor, a deep learning system for offline handwritten text recognition. Offline handwritten text recognition, or HTR, has been a major research challenge for several decades due to its proposal to transcribe cursive text from image to the digital medium. In this context, optical models are responsible for this task and are developed to deal with complex writing scenarios, such as different types of writing, noise images, and unrestricted vocabulary. However, despite the promising results of the DP models existing in recent years, long sequences are also a challenging task due to the vanished gradient problems. The project's objectives are to propose a new gated convolutional recurrent neural network architecture, especially a gated CNN BGRU optical model, where it is able to handle long sentences with different styles, variations, and noise, even in case of limited training data, and able to maintain high performance in recognition even with the low number of trainable parameters. For related works, we brought several state-of-the-art from the usage of hidden Markov models with ADSTM layers to the most consolidated today, such as the Puisiver and Bluche works, using the convolutional recurrent architectures. We selected the works of Puisiver and Bluche to compose the experiment of this work, considering that both are based on the structure of the CRNN model and have high performance in the state-of-the-art. The HTR Floor, our optical model, is based on the good architecture ideas of Puisiver and Bluche HTR systems. More precisely, our model is a neural network based on gated convolutionals and bidirectional gated recurrent units, or gated CNN BGRU. We use the gated mechanism to extract more relevant features instead of using traditional convolutional layers. In the end, we use BGRU for better propagation of information in the recurrent block. In this way, we created a compact and robust optical model with thousands of parameters instead of millions in case of previous works. We choose 5 datasets to carry out our experiments of this work. They are Bethlehem, IAM, Rhymes, Sengal, and Washington datasets. The experiments were performed with the metrics commonly used by HTR research field, the character error rate, CER, and the word error rate, WER. We used the Google Colab platform to perform the various simulations of the optical model. In addition, in order to make a fair comparison between the models and statistically validate the results from the same perspective, we followed the same workflow and hyperparameters for the optical models. Our proposed optical model achieved significantly better results in all datasets in both metrics. Here, we highlighted the results of the Washington dataset because even with the challenge of dealing with few training data, the proposed model still maintained high performance, demonstrating its robustness for this type of context. To consolidate the results obtained, we consider all the results, including all the model training runs, to compose the final results of each optical model. Thus, the HTR Floor outperforms the previous models considering all the datasets presented. Here, we can see some results over 2 selected samples of Bethlehem and IAM dataset, respectively. Now, some results of Rhymes and Sengal, respectively. Finally, an example of Washington dataset. To conclude, we achieved the object of this work in proposing a handwritten text recognition system based on a gated convolutional recurrent neural network architecture, where the presented optical model reached an average value of 3.85% and were of 12.23%, considering all datasets. This represents 3.23 and 6.79 percentage points of improvement to the Boucher model, and 3.87 and 6.48 percentage points of improvement to the Percival model for SIR and WER metrics, respectively. This means an average of about 33% improvement in the recognition rate. Furthermore, the proposed model achieved very good rates even in case of small datasets, reaching up to 80% of improvement in comparison with previous work. I'd like to thank you very much. My contact is available to answer any questions and contributions to our research. Many thanks for University of Pernambuco, CAPES, and CNPq to support this work. Thanks to the organizer of SIBGRAPI 2020 and everyone listening this talk. Thank you so much.
Any questions? Unfortunately, the author of this paper is not present in this session. If you have any questions, please, you can send by the WOVA system or contact directly the author. I'm sure he will be glad to answer your questions. The next paper is entitled Faster and Accurate Compressed Video Action Recognition Straight from the Frequency Domain, and will present by Samuel Felipe dos Santos. Let's watch the video.
Hello, my name is Samuel, and on behalf of Jurandir, I will present our research paper entitled Faster and Accurate Compressed Video Action Recognition Straight from the Frequency Domain. In this work, we focused on the task of recognizing human actions in videos. It is a very important task, having a large range of applications like surveillance, medical, industrial environments, and smart homes. Most deep learning methods are designed to process video as RGB image sequences. However, video data is often stored in a compressed format. Since the videos are compressed, it is necessary to decode them in order to obtain the RGB images that are commonly used as inputs to the CNNs. But this process demands a high memory and computational cost. To address this issue, we propose the FastCoVR network. It exploits relevant information pertaining to visual content available in the compressed representation, saving the high computational loads of fully decoding the video stream. Our starting point was the CoVR method. The method operates on data available in videos compressed on the MPEG-4 standard. It is a network with 3 streams, one for each different type of data from the compressed video. There is a stream for iframes, a stream for motion vectors, and a stream for residuals. However, even though CoVR was designed to work with data from the compressed domain, the iframes from the spatial stream and the residuals from p-frames need preliminary decoding because they are stored in the frequency domain as DCT coefficients. To deal with these problems, we propose to avoid the computational costs of decoding DCT coefficients by using CNNs designed to work directly on the frequency domain. A version of the ResNet 50 network modified to accommodate DCT inputs was proposed. However, these changes increase the computational complexity and amount of parameters. For this reason, the FBS frequency band selection technique was proposed. It reduced the computational complexity of the network by selecting the most relevant DCT coefficients. Our approach is called FastCoVR. It has 2 streams, one for frequency data and one for temporal data. The frequency stream feeds DCT coefficients from iframes to the modified ResNet 50 with FPS. The temporal stream feeds motion vectors from p-frames to a ResNet 18. we experimented on two datasets, the UCF 101 dataset and the HMDB 51 dataset. Here we can see the comparison of accuracy and computational complexity between a few networks and our model. The variations of FastCoVR has the lowest computational complexity amongst the compared methods, while having the second best accuracy for the UCF 101 dataset and similar performance to the other methods in the HMDB 51 dataset. In a comparison with state-of-the-art compressed video-based methods, our approach was able to obtain similar accuracy. The figure compares classification accuracy and the inference time for FastCoVR and CoVR. FastCoVR was up to 2 times faster than CoVR. In this work, we proposed a novel deep neural network named FastCoVR. It was designed to operate directly on frequency domain data, learning with DCT coefficients. Recognition performance was similar to state-of-the-art methods, while the inference speed was up to 2 times faster. Conclusion: FastCoVR is both faster and accurate. Thank you for your attention. If you have any questions, please do not hesitate to contact us.
A very interesting presentation. Any questions from the audience? Okay, I have one question. Samuel?
Hello.
In your paper, all the experiments were conducted on videos encoded in MPEG-4 format. My question is, could your approach also be applied to other video formats?
We could apply to other formats that use DCT coefficients and motion vectors.
And have you tried to extend to other formats?
We only tested with MPEG-4 videos.
Okay, thank you. Any more questions from the audience? Okay, thank you, Samuel. If you have any questions, please, you can post by the chat on YouTube or by the woven system. Let's watch the third video for the paper entitled Counting Vehicle with High Precision in Brazilian Roads Using YOLO V3 and Deep Sort.
Hi everyone, my name is Adson Santos, and today I would like to invite you to know our work on counting vehicles with a high precision in Brazilian roads using YOLO V3 and Deep Sort. Our work helps the Brazilian National Department of Transport Infrastructure, the NIT, to maintain the National Traffic Counting Plan. Why we have a National Traffic Counting Plan? This plan is essential to evaluate the current flow of traffic on federal highways and to define public policies. However, this department still performs a quantitative classificatory service, not automated or with invasive equipment. It's crucial for conducting traffic studies to search for more modern solutions to accomplish a higher number of automated non-invasive and low-cost classificatory service. Our paper proposes a system that uses YOLO V3 for object detection and Deep Sort for multiple object tracking, as you can see in the video. In our experiments, we obtain a precision above 90% in global vehicle count from the results of real-world videos collected in Brazilian roads. We also show that our proposal outperform the other previous solutions with 99% precision in public datasets. We believe this proposal allows the development of a traffic analysis tool to be used to automate the volumetric traffic service, enabling to improve the DNIT agility. So, with that, we can generate economy for the public coffers. Thank you.
Any questions from the audience? No questions. Okay. If you have any questions, please post by chat or by the Hova system. Let's watch the next video for the next paper entitled Luminance Ratios for Stable Shift Key Point Detection in Challenging Illumination Scenarios presented by Lucas Andres.
Luminance ratios for stable shift key point detection on challenging illumination scenarios. Illumination variance is a desirable and important feature for artificial vision systems, especially for controlled illumination environments such as outdoor applications. Therefore, improving robustness of key point detection is the main goal of this work, especially regarding underexposed scenes. Once overexposed scenes can be avoided via adequate camera settings, such as auto irons, without losing information or increasing noise. In order to achieve this goal, the lightness constants concept, based on luminance ratios, first introduced by Hans Wallach, was explored. Lightness constants is the perception of an object to have the same lightness regardless of differences in illumination. For Wallach, lightness constants is achieved by using luminance ratios instead of luminance differences, which is usually adopted for most feature detectors. In order to implement the ratio-based approach, the safety detector framework was adapted. Safety's original difference of Gaussian operator uses differences between scale space levels in order to detect edges. A straightforward way to implement the ratio-based approach is by using the logarithm property shown in the equation. Therefore, it is possible to build a logarithmic scale space from the original Gaussian future images. And by using the logarithmic property, subtracting nearby levels from the log scale space, the desired ratio-based pyramid can be accomplished. In order to investigate an optimal value for the logarithmic base, 8 different values were used in the experiments. The experiments were conducted comparing the proposed ratio-based approach with 8 different logarithmic bases and the original difference-based safety detector. For evaluation, a repeatability score and the number of correspondences for 40% overlap error were used. 3 experiments were conducted, the first with synthetically designed images, and the other 2 using real-world images from the FOSS dataset, which was made especially for experiments regarding illumination changes. One experiment using uniform lighting conditions, shown the top row of the figure, and the other using non-uniform illumination scenarios, shown the bottom row. As expected, the proposed approach had better performance for underexposed conditions. For uniform illumination and underexposed images, larger logarithmic values provided better results for both repeatability score and number of correspondences. On the other hand, despite showing better repeatability score than the difference-based approach, for overexposed images, the number of correspondences was affected. Regarding non-uniform illumination scenarios, which have more resemblance to uncontrolled illumination environments, the ratio-based approach achieved up to 20% better repeatability score and 35% more correspondences than the original SIBGRAPI implementation. Overall, the proposed ratio-based approach was able to detect more stable key points than the original SIFT, which can improve the reliability of current applications with minimal implementation efforts. Thank you.
A very interesting presentation. Any questions from the audience? Okay, I have one question, Lucas. In the paper, you focused on the SIFT key point detector. My question is, could your approach also be extended to other key point detectors, for instance, those based on deep neural networks?
Yes, it could be extended to other detectors such as Sobel, edge detector, Harris corner detector, SURF, and others. Talking about neural networks, I imagine it could also be used but more like a pre-processing step.
Thank you for the question. Have you think about using on neural networks? For instance, I don't know if you have you heard about MonkeyNet? Is a network for tracking and tracking key points on images.
No, we didn't. We used Sobel for the first experiment, but neural networks we didn't touch yet.
Yeah, maybe it could be an interesting direction you could explore.
Yes, yes. We'll see later.
Thank you for the answer. Any more questions from the audience? Okay, so thank you, Lucas. Let's watch the next video. If you have more questions by the end of the videos, all the papers, we can return and open for questions if you have time again. Okay, let's see the next presentation is entitled Performance and Error Analysis of Recursive Edge-Aware Gaussian Filters on GPUs by Hermes Ferreira.
Hello everyone, I am Hermes Ferreira from the Institute of Mathematics and Statistics at URGS, and I'll be presenting our work, which was done in collaboration with the Institute of Informatics of the same university. The edgeware Gaussian filter is a filter that smooths the image while preserving high contrast edges. This type of filter is challenging to implement, especially for real-time applications. In our approach, we use a recursive filter. This is important when we filter high-quality images, since the execution time will scale linearly with the image size. Our contribution is that we achieved a real-time solution for the Gaussian edge-aware recursive filter, which we believe to be the first implementation of such filter. This is an important aspect of our work because since we do not have other approaches to compare to, we chose to make two implementations. The first one is what we consider to be the naive approach, which we call the standard approach, and the second implementation, which is an improvement over the first implementation. Our work is devoted to studying the consequences of using the improved approach in terms of speedups and quality of filtering. Here is an example of what the filter does to an image. To the left, we have the unfiltered image, and to the right, we can see that it has been smoothed, while the important edges are still present. So to understand our work, we need to understand a bit of the GPU architecture itself. The GPU is composed of SM cards, which are the streaming multiprocessor cards, and these cards contain the processing cores. The GPU has a hierarchical structure. It has a global memory, which each of the SM cards has access to, and the shared memory, which is individual for each of the SM cards. When filtering on the GPU, we want to make use as much as possible of the shared memory because it is faster. So what we do is that we split the image into stripes, and each SM card is assigned a stripe to filter. So we chose the height to be simply the number of processing cores in the SM card. And what we do is that we set a block here, read the image into the shared memory, filter it, and travel forward. This approach has shown to be effective, but it does not scale well with more SM cards. This is because the image can only be divided into a limited amount of stripes of same height. Our proposal is to improve the first implementation by allowing more SM cards to filter the same stripe. Originally, SM2, for example, would need to wait for SM1 to complete its filtering process so that it could obtain the initial conditions for this boundary. So instead of waiting SM1 to filter, we choose to use an approximation scheme on this boundary. What we do is extend the length backwards and start filtering from there. Then this extended length becomes an important parameter in our implementation. In our work, we concluded that increasing the length of the approximation reduces the error exponentially, and so we were able to choose an appropriate length so that we could see no approximation effect, and we are also able to reduce the execution time of the naive approach by nearly half. We conclude that our algorithm is appropriate for powerful GPUs, allowing for high-quality image filtering in real time. We would like to thank our sponsors and everyone that helped with our work. And we also thank you for your attention.
A very interesting work. Any questions from the audience? Okay, I have one question. Ernst, roughly speaking, Gaussian filtering is like a convolutional operation, right? In this sense, my question is, could your approach also be extended to speed up convolutional operations performed by convolutional neural networks?
I would say no, because it is a good question, but I would think the answer is no, because the convolutions performed by neural networks, they are usually already small and very fast, and it is more of they are more using a compact filter. So the main idea of using a recursive filter is to use a filter that has a infinite impulse response. So the purpose is also a bit different.
Oh, I see. Thanks for the answer. Any more questions from the audience? Okay, so we have time. As we have time now, we have some authors had some problems with the connection. Now they are present here, and then I will open for the questions. For the paper, the first paper, HTR floor, the author Byron. Any questions for this paper? First paper, HTR Floor, a deep learning system for offline handwriting text recognition. Okay, I have one question, Byron. My question is, in the paper you claim that the same workflow and hyperparameters were applied to all approaches and data sets. My question is, how did you choose the hyperparameters you used in your experiments?
Okay, thank you, Jurandi, for your question. May I have answered the question in the WOVA app, but I can repeat the answer now for the attendance. So they were chosen based on pretests in order to achieve the best result in the shortest training time. In this case, a high learning rate combined with reduced LR on plateau and batch size of 16 images. Another approach would be to adopt long training time, smaller learning rate and batch size of 8 images, for instance. But we also saw in the preliminary simulations that in addition to the high time, the result was equal or less than the short approach. So this is the answer.
Thank you for the answer. Any more questions from the audience?
Thank you for this opportunity, Jurandi, because I have trouble to find the link to the live stream.
Oh, no problem. Yeah. We are in a different time and different type of conference.
Yeah.
And we all understand. Okay, no more questions. Thank you, Byron, for your paper and for
my pleasure
being available here. So for the next paper, faster and accurate compressed video action recognition straight from the frequency domain. Any more questions for this paper? Any questions from the audience?
No questions.
Okay, so for the next paper, counting vehicle with high precision in Brazilian roads using YOLO V3 and deep sort. Any questions for this paper? Any questions from the audience? Okay, so I have one, Adson. And my question is, actually I have two questions. My first question is, if I understood well, you are performing the detection and tracking steps independently, aren't you? Is that correct?
Hello, good afternoon. Thank you for your asking. Yes, you are correct. We have two steps with two different models, but one depends to the other. The YOLO V3 make the detection and send the bounding box to the deep sort, make the tracking of the bounding box in the scene to make the vehicle count. Yes, you are right. This work is independently.
Have you ever tried or think about training those two steps together in an end-to-end fashion?
If I have tried to make it with an end-to-end fashion, we didn't this, but I think it's a good idea. I don't know how to make this. I need to study more about how to make the CNN, the YOLO, learn the hyperparameters, and in the video with so many frames in the train step. But I think your suggestion will improve the solution. I think it's a good idea, and thank you for it.
My second question is, in the results, you compare the precision of your approach with other methods. And what about the number of double counts and false negatives? Because for your application,
Yes.
those metrics seems to be very important.
Yes, I agree with you. This is very important. But these work related don't make the algorithms available. So we only use the same data set, and the results showing in the paper to make the comparison. So the related authors don't show these metrics in their papers. So unfortunately, we can't compare these important metrics, but we show these metrics in our paper because we know that this is so important to make some comparisons.
Okay, thank you for the answers. Any more questions from the audience? Okay, no more questions. Thank you, Watson.
Thank you for the opportunity.
You're very welcome. For the next paper, luminance ratios for stable shift key point detection in challenging illumination scenarios. Any more questions? Any questions from the audience? Okay, no questions. For the last paper, performance and error analysis of recursive edge-aware Gaussian filters on GPUs. Any more questions from the audience? No questions? Okay, so I think we can end this section. Thank you very much for your attention. Thank you very much for watching this section. I hope you have enjoyed it. Next, we'll have interesting sections and presentations and keynote presentations. I hope you enjoy the rest of this conference. Thank you very much.